All right. I'm actually going to have my webcam off for a good portion of this chapter because a lot of the slides just have so much stuff on them that my webcam just covers it up. So I'll be turning that off anyway for most of it. Okay. All right. So aside from RIP v2, EIGRP is the youngest interior routing protocol in the sense that it's from 1992. And so what that means is it was designed after we learned a lot of lessons from the other interior routing protocols. Okay. It has features that none other like OSPF doesn't have, ISIS, including unequal cost load balancing, right? So that's where, we've got multiple paths to a destination. And we pick the one with the best metric, which usually translates to like bandwidth or whatever, right? But what if you have two paths and one of them maybe isn't as fast as the other one? But does that mean it's not totally usable? I mean, couldn't we load balance a little bit? And that's what unequal cost load balancing does, is it allows you to use unequal cost paths and load balance. And so you load balance in proportion to the metric, right? So if you have say 100 megabits per second and 50 megabits per second link, all right? Well, it'll for every one bit, megabyte, packet, whatever, it'll send two over here. So they're proportional, right? So this essentially has 1/3 of the bandwidth, and this has 2/3 of the bandwidth, and you add them together, and you have all the bandwidth. Okay. So on the left, it's twice as fast, so it has twice as much traffic, which equates to 2/3 of it. Unequal cost load. For that are really large and super fast, even immediate convergence. So EIGRP. So talking about EIGRP, I'm going to sound a little bit like an EIGRP fanboy, especially when we compare it to OSPF. So let me just say right now, this has nothing to do with the fact that it's Cisco proprietary. Cisco has actually opened it up. EIGRP is now a published open standard. Cisco still maintains control of it, okay, but they've opened it up so other vendors can use it. However, that was only done a few years ago. So because OSPF is older and is an open standard, whereas EIGRP was proprietary up until just a few years ago, OSPF has been deployed much more widely historically. And because of that, more engineers know OSPF. And if you're designing a network, what are you going to deploy? What you know and what you're good at. So because of that, OSPF is much more widely deployed than EIGRP. However, from a technical standpoint, and that's not always the only consideration when you're designing a network. If all your employees know OSPF and they don't know EIGRP, you may want to rethink deploying EIGRP. You're deploying a big tool that controls your network and your staff doesn't understand it very well. Not the wisest choice. However, if we're just looking at the technical elements of EIGRP versus OSPF, I think technically EIGRP is much more scalable. It hammers the CPU a lot less. It's vastly more flexible. Okay, you can summarize wherever you want on what interface you want. It doesn't have to be ABRs. You don't have to divide your network up into a strict two-layer hub and spoke kind of network like with OSPF, where you've got the backbone and then all the other areas. And it can have immediate convergence for backup routes, where if a route goes down, we can slam a route into the routing table immediately if the conditions are right. Okay. So with all of the and the fact now its major shortcoming was that it was proprietary and you had to use it on Cisco equipment. Other vendors now support it, and so its major detractor has been removed. So purely from a technical standpoint, I honestly feel EIGRP is a superior routing protocol than OSPF. Its major problem is that OSPF has been so widely deployed. It is what people know the most. So OSPF is what you're going to experience out in the wild. However, like I said, EIGRP from a technical standpoint, I think is much better. It's much more customizable. But of course, with great power like that comes great responsibility. It's kind of like the Apple OS versus Windows, right? Traditionally, and this is less so these days. Apple has mitigated some of this, but traditionally, Windows was much more configurable, right? But if you misconfigured something, you could break it. Apple, on the other hand, um, was a lot more, it just works, but you couldn't tweak it. You couldn't customize it because it kind of protected you from yourself. It just works, right? Windows is like, well, it works, but you kind of got to get it to work. Again, Windows has moved more in the direction of it just works, and Mac has moved more into the direction of now you can customize more, especially with the command line. Um, that's kind of OSPF versus EIGRP. OSPF is you have to have a backbone, and then you've got, you've got the backbone area, and then you've got the other areas that connect to the backbone. Um, and these areas cannot connect up to each other at all. This is the topology you have to do. And as long as you follow this topology, which you have to do, then it's going to solve a lot of your problems. With EIGRP, you do not have that kind of restriction. You can have whatever the heck topology you want. However, if you design it poorly, you can cause yourself a lot of headaches that OSPF would protect you from, right? So it's kind of like EIGRP gives you a lot of choices, but you really should know what you're doing. Now, that's if you get into the advanced settings, which we'll talk a lot about advanced EIGRP setup kind of going throughout this course. Um, so so with that said, I will be pointing out as we come across these things where I feel EIGRP is superior. And again, it's almost like a futile exercise on my part because when you guys go out in the wild, you're probably just going to work with OSPF unless you're in a Cisco shop, right? That's just all Cisco, which they do exist. But even places that deploy only Cisco have sometimes hesitated to do EIGRP because they were afraid of being locked in. They wanted to have the choice of going elsewhere, so they end up deploying OSPF. And now that EIGRP is an open standard, well, their network is already OSPF, right? So I'll be pointing these things out, but really OSPF, you want to make sure that you understand OSPF. Oh yeah, and another thing I just thought of, EIGRP is much simpler in the sense that you don't have to learn about all the different LSA types and things like that, right? So, all right. We have the diffusing update algorithm, or DUAL, which is what we use to find loop-free backup paths that are ready to go in case we need a quick change. Okay. I don't get it. Okay, so autonomous systems. So we have Widgets Inc. on the left here with EIGRP as the routing protocol, autonomous system 100. Okay. Then we have Sprockets LLC, which is also using EIGRP, and it has AS 200. Okay, so remember the autonomous system is a common routing domain. So one kind of administrative authority has control over a group of routers. I know that's kind of a weird way to say it, but sometimes it can be separate companies or separate departments. Okay. So in this case, we have two separate companies. Both are running EIGRP as separate routing domains or autonomous systems. Okay. Now, one company buys the other one. Okay. Widgets Inc. buys Sprockets LLC, and they're going to link their two networks. Okay. But we have two separate autonomous systems running. And as far as EIGRP goes, the router in the middle is going to run both autonomous systems at the same time. And we are going to have to do route redistribution, in order, say we have a subnet over here, and in order for this router to know how to get there, the route for this subnet has to be redistributed into AS100 so that this router has a route to it and knows what direction to go. Okay. So we'll talk more about route redistribution in future chapters. We'll come back to this. It's one of those things that it's not super common, but it happens enough that you need to know about it. Okay. So any router that's in the same domain is going to use the same metric calculation. We're going to exchange routes with routers in the same autonomous system. Okay. But this is one of those times where we're using vocabulary in a way that could be confusing. Autonomous system here, we're talking about administrative authority over a group of routers. All right. This is not the same thing as the autonomous system number that IANA assigns to companies for BGP and internet use. All right. So don't confuse those two autonomous system terms. So we have autonomous system, meaning a group of routers that we control, and an autonomous system that means this is your autonomous system number for your BGP instance to communicate on the internet. Two separate animals. All right, so let's talk about the basics of EIGRP fundamentals. Okay. Here's the topology. So we have routers 1, 2, and 3. Okay. The LANs are 172.16 and 2, so it's .2, R3, 3, R1, 1. Okay. So 172.16 is the LANs. And then we have the 10.1, which is the links. And from router 1 to 2, it's subnet 102. From router 2 to 3, it's subnet 203, and then 103. Okay. Notice we have 1024 kilobits per second, T1 speed over here, 64K over here. Okay, so that's the topology. All right, so here's our initial config. So we've got 3 interfaces that we're going to configure. Okay. So we've got IP addresses. Okay. And then on serial 001, we're setting a clock rate because that's the DCE side of things. And then notice we're setting the bandwidth, 64K. And if you before you do the number, hit the question mark, and it'll tell you to put it in kilobits per second. So just 64, not 64,000 or whatever. Okay, so 64 and then 1024 for that link. We're going to do the same thing over here on R3. We basically are doing that on R1, R2, and R3. Strictly speaking, that command bandwidth 1544 isn't really required because that's the default bandwidth for a serial connection. Okay. And again, does anybody remember what the bandwidth does? What is the purpose of changing the bandwidth connection?
Is it for the metric?
Yeah. So the bandwidth doesn't actually change the bandwidth of the interface. All it does, it's used to inform the routing protocol what the bandwidth is for that interface in order to properly calculate the metric. So we wouldn't have to put the bandwidth on, like, say, those two interfaces. All right. But the default bandwidth would be used for the metric, and we would not be making optimal routing decisions. So we need to tell the routing protocol what the correct bandwidth is to use. And again, that's the default for serial 1544. Okay. All right, so now we have the interfaces configured with the bandwidths on them, IP addresses on them. Oh yeah, and then again we've got the clock rate set on serial 000 for R3, and that's because that's the DCE side of the link. Normally the service provider sets DCE, but since this is kind of a lab-like topology, we're doing it. Okay. So we have our network command. So just a reminder, can anybody describe what the network command does? What is its function? How would you describe it?
You advertise?
Yes, it does lead us to advertising, but how does it accomplish that? Any ideas?
The instances.
So, well, what it does essentially is it tells the routing protocol what interfaces are going to participate. That's it. So, at least in a direct sense, it does not tell us what to advertise. It leads us there indirectly. So now in this case, in this command here, we don't have a subnet mask, so that means it's classful. Okay. So essentially, what we're going to do is we're saying, look at the assigned IP address on your interfaces. And is that IP address, not the subnet, the IP address itself? Okay, so for R1, we're saying anything that's in 172.16/16 needs to participate, right? So that's that one, 172.16.1.1. And then 10.0.0.0/8. So everything in the 10 dot network, right? So that's these interfaces. Once the interfaces are participating, so notice this one command is making two interfaces participate. Now those interfaces are going to send and receive hellos, and we are going to advertise the subnet that those interfaces are assigned to. So this command is going to cause us to advertise this /29 and this /29, as well as this /24. We don't have this. That's a /24. So keep that in mind. That it's like we're splitting hairs, but it matters, right? Instead, we could do all zeros, and then we'd have to do a wildcard mask of all 255s. And that would be the equivalent of kind of like a default route, right? All IP addresses are going to fall into that. So all zeros and then all 255s are going to say all interfaces participate. Or you could do a /32, right? Here we could do, network 172.16.1.1, and then do a /32, okay, which would be all zeros in a wildcard mask. And then that would tell this to participate. Now, me personally, I probably wouldn't use those network commands as my first choice. I might use the actual network. However, that also is not my first choice. My first choice would be to use the default route method. It's not really a default route, but it's the equivalent, right? Now, obviously, that only works if literally all of your interfaces are participating, right? If not all of your participating interfaces are participating, then you don't want to do that. So my next best one would be the /32. And the reason is because if you make a mistake and a typo, it is much easier for somebody to come after you and see what you were trying to accomplish, right? If you're using some wacky classful network or some combination of weird things, it can be hard to troubleshoot. But if you do a two on all of them, it's what you were trying to do, or the default route method, right? It's clear what you were trying to do. Just have all the interfaces participate. Okay. So R2, we're kind of doing the same thing. R3 now we're doing the actual network 172.16.3.0/24, and then we're doing the /29, right, for those two. And just a reminder, again, the a /29 has a subnet mask that ends in .248. So if you take 255, 255, 255, 255, subtract out the subnet mask, you will get the wildcard mask. All right. Now we're going to configure the router ID using the router ID command. And we can see an example here with R3. We change the command and we lose the adjacency, but then it comes back up because we changed the router ID. Okay. Now, although I said we don't have to deal with as many LSAs as OSPF, we do have basically 5 packet types like OSPF. We've got the hello and the acknowledgement. Okay. These are not sent reliably, which means we do not acknowledge hellos and we do not acknowledge acknowledgements because that would cause problems. So we have an update message. All the rest are sent reliably. Okay, we have the update, which sends routing information. We have a query, which asks for routing informations. And then we have a reply, which responds to a query. All right. So obviously, hellos are going to be sent back and forth to discover and form adjacencies with neighbors. They're usually multicasted to 224.0.0.10 or FFO2::A. And remember, A is hexadecimal for 10. I have seen it erroneously in some places saying it's going to FFO2::10. Okay, that is not correct. It's A, which is hexadecimal for 10. All right. And again, sent unreliably, we don't acknowledge them. One of the most important commands is the show IP EIGRP neighbors. And this goes for OSPF too, or even BGP really. One of the first things that you need to do when you're troubleshooting is verify that the neighbor relationship is up, because the first thing that OSPF routers are going to do is create adjacencies, right? From there, we're going to exchange routes, and those routes are going to go into the topology table, and then they're going to get offered into the IP routing table. So if you're troubleshooting, that's a good order to look stuff in. Are neighbors the way they should be? Are the routes that we're looking for in the topology table? And then are they in the routing table? Okay. So the show IP EIGRP neighbors command is going to show us our neighbors. So here is the IPv4 address of the neighbor. Okay. And that is the next hop address to that neighbor. That's not the router ID. Then this is our local interface. Okay. This is our interface that we issued the command on. This is how long the hold timer will stay up. Remember, that's counting down, and if it reaches 0, that means we've missed enough hellos that we're going to consider that neighbor down. Okay. How long this neighbor was added to the neighbor table, this gives us a sense of stability, right? All right, so here we're looking at R2. We can see that with this command, the show IP EIGRP interfaces. this gives us a little bit different information. This is telling us, okay, again, remember, whenever you look at these commands, they're hierarchical in nature. All right, so we're saying, show me something, right? Show me IPv4 related stuff, specifically related to EIGRP. And then more specifically, interface information related to EIGRP. Okay, so this is going to show us all the interfaces that are participating. Okay, and how many peers we have. So here we can see that gigabit 00 is participating, but we don't have any neighbors going that direction, which makes sense. There's no routers there. Okay, we can add the D and get a lot more information on each interface, right? So here's serial 00, 0. And the rest of the interfaces that are participating would show up. Okay. So we can see, you know, the hello and hold time. Now with OSPF, the hold time is 4 times the hello. With EIGRP, it's 3. Okay. We can see we've sent a couple thousand hellos. We've sent 4 expedited hellos. When startup happens and the interface comes up, we just send some expedited hellos, just boom, 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 boom. And then we go to the hello interval every 5 seconds. Okay. The hello packets for EIGRP are very, very small. And depending on the interface, we're going to send them by default every 5 seconds, except for T1 or slower non-broadcast multi-access networks, such as the serial links here. They're going to be sent every 60 seconds unless you were to change that. Okay. Oh, I'm covering up the. So remember this. This is if we have there. So in DMA, you know, for example, you are slower, 60, and then the whole time is 3 times that, 180. Okay. If it's greater than T1 speeds, 1.544 megabits per second, so not including T1 speeds, but faster, then it's going to be 5 seconds, right? Not really sure T1 should be in there. That's kind of confusing. All right. So now if we do, hold on. Let me fix this. I think we're missing the top of the slide here. Okay, now I'm just not showing it. So if we do show IP protocols, okay, and then we get to the EIGRP section. Again, you know, we've got our router ID, we have our distances, maximum path, maximum hop count, maximum variance. We'll talk about these things going forward in the next, you know, few chapters. All right. Automatic summarization is disabled. The networks that we're routing for, right? I actually forgot. I should use my little pop-ups. There's the process ID, the router ID. That's the maximum hop count, which is not a metric. The variance for unequal cost load balancing. We'll talk about that in a bit. Auto summarization is off by default on modern iOSs. Here are the networks that we are routing for. This is actually the network statements. Okay, so this isn't saying what networks we're advertising, because that's based on what's assigned to the interfaces. No, this is saying what we are advertising, or what the network statements were that actually got typed in. And then here are our neighbors. Okay, now we know that we don't want to send hellos when there's no reason to, right? There's no router here. So we don't want to send hellos because it's just a waste of resources and bandwidth, and it represents a security risk, right? If a router were to ever show up there, we might actually form an adjacency, which we don't want to do. And that means we're forming a relationship with some rogue router. Okay, so we want to stop that. So what we're going to do is we're going to say, okay, that interface is still participating in EIGRP, but we want it to be passive, meaning not active. Don't send or receive any hellos. Or just let the other interfaces handle everything and advertise your subnet. Okay, so we say passive interface gig 00, and we're going to do that on all three. We can verify that if we do show IP EIGRP interfaces, we can see they are not participating, right? We only see two interfaces here. But now if we look at the show IP protocols, we can see there's a section called passive interfaces. But we're still routing for all we were before. Now what we're going to do is we're going to simulate what happens when this is down. Don't want to actually do a shutdown, okay? Because it brings both ends of the link down. So we want to simulate what happens when your WAN link, the neighbor no longer is there, but the interface stays up. Okay, so what we're going to do is to simulate that in kind of a lab environment, we're going to go into the interface and we're going to say no IP address. So that way, if we did a show IP interface brief, this interface would show us up, down. It's up at layer 2, but down at layer 3 because there's no layer 3 address. All right, so this way it's still up at layer 2. Okay, and so now we can kind of see what's going to happen if we do a debug EIGRP packet hello. Again, debug EIGRP related stuff, EIGRP packets, and specifically hello packets. Turns on. So we received a hello from R1. Remember, we're on R2. And then we did this on R1, which means now that that's down at layer 3, well, routing is a layer 3 concept. If the interface is down at layer 3, we're not routing on that interface anymore. Okay, so we're no longer going to receive any hellos from that interface. Okay, so you can see now the green arrow, we're sending hellos, sending. We've missed 3 hellos, and the dead timer is going to expire here. Then we can see the neighbor is down. Okay, so these debugs can be really helpful in seeing what's going on. Okay, now if we would have just issued a shutdown command on that interface, it would have gone down, and then this one would have gone down too, and we wouldn't see any of this output. In this example, we're going to debug all EIGRP packets, not just hello packets. All right, we're going to enter a network command. So on R3, 10.1.203. So let's say that wasn't there, and we're going to start basically saying, okay, interface, you are now participating in EIGRP. So we can see it's sending a hello, it's received a hello. We have a new adjacency because we've received a hello, we've sent a hello. Now we're going to send an update. Then we're sending the update. We've received an update. We're acknowledging the update. We're sending that acknowledgement. We have also received an acknowledgement to our update from up here. Okay, so you can watch this happen in real time. If we look at the traffic counts, show IP EIGRP traffic, we can see the hellos, queries, updates, right? So hellos sent, hellos received should be relatively equal. That does look kind of off. So maybe the other side was down for a little while, right? But you'll notice the queries received match the replies sent, and the queries sent matches the replies received, right? So that makes sense, right? All right. So now let's look at everything from the perspective of R2 up at the top there. Okay. So we do show IP route EIGRP. So show me IPv4 routing information, but only the EIGRP routes. Okay. So we're just going to see, D's down here for dual. All right. So we can see this subnet right here from R3. So it's being advertised to us. So let's talk about how do we make routing decisions using dual. So what does dual do? It's the algorithm used by EIGRP. Okay, it determines the best loop-free path as well as loop-free backup paths, which can be used immediately. If the best path goes down, we can use those backup paths immediately. Like it's ready to go. We slam it into the routing table so fast that if an interface goes down and we have a backup path ready, it can go into effect quickly enough that we may not even drop any packets. Okay, so fast convergence. Okay, minimum bandwidth usage with bounded updates. So bounded means they only go where they're needed to go with requests and stuff. We also have, now this is the part that gives people the most problems, right? If the OSPF biggest complicated thing was the link state advertisements, for EIGRP, it's the successor, feasible distance, feasible successor, reported distance, feasible condition, or feasibility condition. Okay, so let's talk about those. Okay, but first, let's kind of see how this operates. All right, so we've got R1, R2, and R3 in this network. We introduce this router right here, and it has that 10 dot network. It's going to advertise that network. R3 is going to get that and is going to say, okay, I can get to the 10 dot network with a metric of 100. And obviously EIGRP metrics are much larger than that, but this is just to keep it simple. R1 gets it advertised too and says, okay, so to get to the 10 dot network, I will use R3 to get there as my next hop, and it has a metric of 120. All right. Now say we've got this, router A and router B gets added. Okay. Router 2 says I can get to the 10 dot network with a metric of 300. Okay. So the question here is, clearly R2 is going to advertise that it can get there. Is R2 a valid backup for R1? What do you think? Can R1 use R2 as a backup to get to the 10 dot network? Do, 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 do. No. Okay. Exactly. Why? Why can't it? Because, R1 advertised. Yeah, because like R2 has to go through R1. Okay, so this is an important concept. It is a loop, right? If a router has to go through itself to reach the destination. Okay, so essentially every router has to make sure that no path loops through itself and creates that little kind of cross point there. And each router is only concerned with itself. Does that path loop through me? No router can control loops through other routers. Each router is responsible for its own. Okay. So R1 is going to say, no, I cannot use R2 as a backup because it comes back through me, R1. R2 only knows this route because of me. So that's a loop. All right. So back to this situation. Okay, so R3 can get to the 10 dot network through router X there. R1 says the same thing. I'll get there via R3. Now look at what happens to our network. Is R2 a valid backup for R1? Under this new layout? Yeah, it is. Except here's the problem. We know that because we can see the entire network, okay? And we can tell that R2 has its own path, right? So if R1 went that way, there's not going to be any loop here. Okay, here's the fun part. R1 needs to know that R2 is a valid backup in the sense that it needs to know that there is no loop. But remember, this is not a link state routing protocol like OSPF. This is a distance vector routing protocol. So all it knows is the total distance and direction to get to each one. It doesn't have a map. So how does it know that R2 is a valid backup? It's a backup. R2 is advertising the route, but how does it know that it doesn't loop through it? Okay. Well, okay. So let's do this. R1 knows it can get there one of two ways, right? So this way has a cost of 120 and this way has a cost of 300. Okay, step one. What's the first thing R1 is going to do? It's trying to pick which way to go. What's it going to do now? It's got two choices. What's it going to do? Don't overthink it. It's easy. Yeah, it's going to pick the best route, right? So the best route is 120. Okay. So I'm going to, let's say this line represents a line that is 120 long, whatever that means. Okay. Now, in order for, okay, so now that line represents this line. Okay. Now think about this. Let's say there's a backup. Right. Let's say R2 looped through R1. And look at the length of this line. Compared to R2's, would you say that blue line, almost looks black, is longer than R1? You know, let's remember, we're saying it's 300, right? Notice that's longer. Now, let's say, you know, we're actually in a situation like this. Okay, so now this path is like this. So R2's reported distance is 300. That's not R1's distance if it was going to use that route. Okay, so does R2 loop through R1 right now? No, exactly. It doesn't. But the problem here is R1 can't know that. It can't use this as a backup route because this line is long enough that it could be looping through it. Okay. Now what if all of these were high speed links and this distance was 30? Okay. That would make that line this long. Okay. Now, could this line be looping through the red one? No, because it's too short. Okay. So say this is a really slow link, right? So if R1 went that way, the cost would be 1,000 plus 30, which is why that's not the best link. Okay. That's the feasible distance. That's the distance that R1 would feasibly have to go through if it used that link. The reported distance by R2, is 30. So R2's distance is less than, let's go over here, our best metric. And so because this is so much smaller than this, that one is not looping through. So it's not a loop. So we can use that as a backup route. Okay. So the thing to remember, our best metric compared to R2's reported distance, or R2's best metric. If R2's metric is less than our metric, or if R2's reported distance is less than our best route, it cannot be looping through our best route because it's not long enough. Does everybody get that? Does that make sense? R2's metric is too small. It cannot be looping through us. Therefore, we know it is not a loop. And therefore, we can use it as a backup route.
Yeah, I have a
Okay.
question, when you say looping through, what does you mean?
Okay, so let's say the topology was like this. And we're saying we can get there. Okay. That gets advertised this way, that gets advertised that way, um, the advertisement will actually go kind of both ways. Okay. But let's just focus on one direction. The advertisement goes up here. Now R2 says, hey, R1, you can get to the 10.network/8 through me. R1 is like, oh, okay, I can use R2 as a backup. Okay, well, that means this is, let me change colors. This is the path that it's going to take. If R1 sends a packet, it's going to go like this. It passed through R1 twice. Okay, so that's creating a loop through R1. And so what we're saying is, R1's cost is 120, and R2's cost, is this. But notice this portion of the line is doubling up, right? So that means this line is long enough to be, oh, you know what? Sorry, I'm confusing the issue. Let me, okay. So, but for this portion of the path, these, this line is long enough that it's going through the red line and is a loop. But the issue is, in this case, there is no loop, right? R2's path is not looping through R1. Because remember, we're looking at everything from the perspective of R1. Remember, we are R1. That's all we care about. We are R1. We're looking at the world through the eyes of R1. R1 gets told about this path, and R1 knows, hey, my path is 120. This path is 300. Okay. Well, R2's reported distance. This isn't our distance because we would have to add this length to it. But R2's reported distance reported distance is greater than our feasible distance. That's the distance that, our feasible distance is what our distance is if we were to go that route. Okay. And so because of that, R2 theoretically could loop through that this path is long enough that it might be a loop. Okay, we can tell by this topology. We can see the topology. We can tell it's not looping through, but R1 doesn't know that, right? R1 can't tell that this is the topology, right, versus this. So for all R1 knows, that could be the path, and that's a loop, and we can't have that. Okay, so even though the path is that, we know that there's no loop there, but because this is long, here's the 120, our feasible distance, and the 300, that's the reported distance for R2. This is long enough that we could have a loop. Okay. Again, if each of these were super fast links, then we have our metric, our feasible distance, and then we have the reported distance. This is too short. So this path cannot be looping through us, because if it did, it would have to be at least 120 if it was looping through us. Does that make sense?
Yeah.
Got it. Okay. So remember, the reported distance needs to be less than our feasible distance in order for it to be a valid backup route. Because then we know we can be guaranteed it's not a loop. Okay? And that's the feasibility condition. So R2 can be used as a backup if it reports a cost less than R1's cost through R3, right? This is 120. Notice in this case, R2's distance has to be greater than 120 because it's this link plus ours, right? Over here, though, it in theory could be anything. But we have a cost of 120. This one has a cost of 300. R1 is not going to use that as a backup. Okay. Remember, EIGRP is a distance routing protocol, so it doesn't see the map as a whole like OSPF. So on the plus side, OSPF can see the map as a whole, but that's also its downside, because when the SPF algorithm has to run, it hammers the CPU like crazy. It has to basically calculate every possible path to every possible destination. With EIGRP, we don't have that kind of calculation, but we also lose the benefit of seeing the network as a whole, which means now we need to rely on this feasibility condition in order to calculate backup routes. Okay. So because we cannot see the entire map, we have to say, okay, we can't tell if the backup route is a loop or not, right? Is it this or is it this? R1 can't tell. So in order to play it safe, we only accept a backup route if it meets the feasibility condition, which I just explained. And I explained it before we got to it in the slides, because I like using those lines, the length of the lines, to kind of illustrate how it works. Okay. So R1 will only use R2 as a backup if R2's metric is less than looking at to get to the 172.16.3/24 network in the lower right. And we can see R2 has two paths, right? We can get there let's draw it the right way. We can get there this way or this way. And of course, So R2 has two choices. And we can see in the topology table, now this is the EIGRP topology table. Remember, first we form the adjacency table, then we form the topology, the EIGRP topology table. Then the best routes here get offered to the routing table. Okay. So here we have this destination, and we can see we have two. One is VMware dot one. Okay, so that's the next hop. So we essentially have this as the next hop and this as the next hop. So we've got two potential paths. Okay. So we've got the red one and the blue one. Now, first thing we're going to do is we're going to pick the one with the best metric, right? This one has the best metric. Okay, so that's the path that we're using. So the question here is this a valid backup? Okay. Well, let's kind of simplify the output and just look at that part of the topology table. Okay. So because the red one has the best metric, that we're going to call that the successor, right? So let's say you were a king, and the or queen, a king or queen, and you're like you've got authority. And what is the symbol of your authority? This packet that you have. Okay. Well, when you're done with the packet, who are you going to pass it on to? Your successor. So the successor is the one that gets the packet after you. All right. In this case, it's 10.1.203.3 R3. Okay. So that's the next hop address of the successor. The feasible distance is our metric. If we were to pass on a packet to that next hop on its way to its final destination, the total distance traveled would feasibly be that distance. Okay. Then we have the reported distance. Okay. That is R3's reported distance. Now for the successor, so the best route, we actually don't care about that. That's irrelevant. This is the best route. It has the best metric, the best feasible distance. So we don't care about the reported distance. Okay, in this for the successor. And then that is the outbound interface. All right. R1 in this case is the feasible successor. Again, we have the next hop address. And then R2's feasible distance if R1 becomes the successor. So if R2 were to become the successor, that's its feasible distance. Okay. So this would be the metric for R2 if it used that route. But this is the reported distance, right? So R1 is basically saying, hey, this is my distance to get there. If we were to use that route, this would be our distance. Okay. So, and then of course, there's our outbound interface to reach the network. So the reported distance is our neighbor's feasible distance to that same network. Okay. So our distance, neighbor's distance. Okay. So R1, that's R1's distance. That is our distance if we were to use that path. Is it clear what the difference is? The reported distance of the neighbor. Oh, sorry, I'm covering that up. Okay. So the feasibility condition says the feasibility condition is met when a neighbor's reported distance is less than the local router's feasible distance to that same network. Okay. So our so this is the feasible distance if we used that hop, but we're not. Our actual feasible distance is that because that's our best path. This path is a valid backup if the reported distance is less than the feasible distance. Okay. That means R3 is the successor and R1 is the feasible successor. It is feasible that they could be our successor at some point in the future should R1 go down. Okay. So R1's reported distance is less than R2's feasible distance via R3. So R1 is a feasible successor. This is small enough that we know it can't be looping through, small enough, it can't be looping through us. This path is not a loop through us. So therefore we know it's a valid backup condition, okay? But if we were to use that link, if that one were to go down, that's what our cost would be. Okay, this is R1's cost. We're R2. This is our cost, right? So R1's cost is the same as the reported distance for R1 because R1 is reporting to us its distance. Okay, so basically R2 is saying my cost to that network is 2 million and change. If this is less than your current metric via your best route, then I am a feasible successor. Okay. R2 says my current metric for the best route or the successor route is 3 million. If my current best path to that subnet becomes unavailable, you will then become my successor. And of course, that metric is, well, let's see, 41 million and change. So really sucky compared to our existing metric, okay? But it's still a valid backup. So on R2, if we were to shut that interface down, R2 immediately, and that's the key, immediately uses its feasible successor. And if we were to do a show IP EIGRP topology really fast, there would only be one in there. This is gone. That doesn't exist anymore. Okay. If we were to do show IP route EIGRP, this path would show up in the routing table immediately. And then if we did a no shut, this one would return. It would take some hellos and some updates and stuff. It would not be immediate, which is fine because we would still use that while it came up. Okay. Now let's look at things from R1's perspective. Show IP route. Okay. So there's that path to that network. If we look at R1 and we look at the topology table, okay, now we know that R1 has 2 valid paths, right? But there's only one listed here. So let's look at that. We can see the next hop, right? That's R3. The feasible distance, R3's reported distance, which since this is the successor, we don't really care about that. It doesn't mean anything. And there's our outbound network, okay? There is no feasible successor here because in order to be feasible successor, R2, right? So if R1 went that way, must satisfy the feasibility condition. Now, remember I said before, the topology table includes all EIGRP paths. So this is a path. Why isn't it here? Well, this command only shows valid links. If we want to see all links, even potential loops, we have to add the all links keyword. Okay. So now if we did the all links keyword, and again, this isn't all the output, just for this subnet. Now we can see that path. Okay. But the reported distance for R2 is more than the feasible distance of R1, which means this path is long enough it could theoretically be looping through R1. We can tell that it's not because we can see the topology. But R1 can't tell that. All it knows is that backup path is long enough that it theoretically could be a loop. So we are not going to use it as a backup path. Does this mean that R2 cannot be used if this path goes down? No. Is R2 can be used, but there'll be a longer delay before it gets added to the routing table. Okay, Dual will need to send a query message to R2 to see if it still has a route. Because think about it. Let's say R2 was looping through R1, okay, and this link goes down. Well, R1 is going to advertise that out, and R2 is going to say, oh, I don't have a link anymore. So then R1 is going to query and say, hey, you reported that you had a link. Do you still? And R2 is going to be like, no, because it was looping through R1, right? Now, in this case, we know that R2 was not looping through R1. So when R1 queries R2 and says, hey, can you still get to this subnet? R2 is going to reply and say, yep, sure can. And then R1 is going to be like, oh, okay, I'll go ahead and put it in the routing table then. Okay. Any questions on the feasibility condition? That's basically it in the nutshell. If the neighbor's reported distance is equal to or more than our distance, they could be looping through us. So we're not going to use them as a backup. Okay. If their reported distance is less than our feasible distance, then their reported distance is so short, it's not possible for them to be looping through us. Therefore, we can have the backup route ready to go. If our primary route goes down, if our successor goes down, we can slam that backup route into the routing table immediately. And this is one of the reasons why EIGRP converges faster than OSPF. Because if it's a case where we have a valid backup route, we can have a link go down and we can immediately be forwarding traffic and quite possibly not even drop a single packet. Is everybody clear on what the feasibility condition is, the reported distance, the feasible distance, successor, feasible successor? You're all clear on that? Okay. I would recommend maybe over the weekend watching this part of the recording again to refresh. This is one of the more complicated things that people have a hard time wrapping their brain around. Okay. Good. Let's talk about timers. EIGRP neighbors with differing timers. Okay. One thing for OSPF, to create a neighbor relationship, the timers have to match. Okay. And that's because you can draw a clock in there. Okay. Okay, with EIGRP, there's no convenient place to make a clock face. So timers don't have to match. No match. Okay. However, if neighboring timers are off by too much, it could cause problems. So we can view that by oh, not sure. My thing's not responding. All right, there we go. Now we're good. Okay. Oh, I'm covering it up again. Wish there was a way I could get you guys control of my webcam so you could turn it on and off. I'll bet you there's a way I could figure out how to do that. But if you type a certain thing in Discord, okay, I'm getting off track. Except my brain's working now. Okay, focus. EIGRP, not whimsical little Discord automations. All right. If we want to see what the timers are set on an interface by interface basis. Okay, so that means it's an interface level command. We want to look at information IPv4 information about EIGRP on the interface, detailed information about a specific interface. Okay. So here, hello is 5, hold is 3 times, which is 15 seconds. Okay. So we can see both of those match. We do IP EIGRP neighbors, right? We can see we've got a neighbor. There's the interface, okay, and there's the hold time, right? If we're sending a hello every 5 seconds and the hold time starts at 15 and counts down, it really shouldn't get to 10 or maybe at 10 for a split second as it gets a hello, right? If it gets down to 5, that means, if it gets down to 7, we've missed 1. If it gets past 5, we've missed 2, and if it hits 0, we've missed 3. So if we want to change the timers, we go into the interface and say IP hello interval EIGRP autonomous system 1, 10 seconds. Now this command will automatically be done at 3 times 3, but it's always a good practice to manually do it just in case. Okay. So here we've got a hello every 10 seconds. The problem is if we miss one hello, then we're going to go a full 20 seconds. And that means missing one hello is going to cause the relationship to go down. So even though we could do this, this is probably not a good combination of timers. Okay. But if we wanted to verify that our change held, we can see that here. We can see that we still have a neighbor relationship. But again, like I said, if we miss one hello, the relationship is going to go down. Okay. So how does the hello thing work? Well, the first thing that we're going to do if we're trying to establish a relationship is we're going to say, hello, I'm a router who's on the link. The next router is going to see that hello, and that hello is going to tell router B that router A exists. And it's going to populate its neighbor table with router A's information. And it's also sending hellos as well. So neighbor A will eventually learn about neighbor B. Okay. Once they find out about the other neighbor, they're going to send an update. Here's my routing information. Okay. And router B heard about router A first, so it's going to send a hello. We're not wasting time with an election or anything. Just you find out you got a neighbor, send them your update. And then, of course, number 3 there, router A is going to acknowledge that information, okay? And it's going to populate its topology table with the information that it got. And it's also going to send that information to router B, who's both going to acknowledge it and populate the information. At that point, both routers are going to take that information from the topology table and offer any routes up to the routing table. And then depending on what's in the routing table, it'll get installed or not. And then we say they have converged. Okay. How does the path metric work? Okay. One of the reasons, and I said this before, the administrative distance the other day of EIGRP is lower, because remember, lower distance, better. One of the reasons the administrative distance of EIGRP is considered lower is because we prefer EIGRP. And that's not just because EIGRP is proprietary to Cisco and Cisco loves Cisco, right? No, it's because EIGRP, theoretically, it takes more information into account when calculating the metric. And therefore, the theory is that it is a more reliable measure. So the administrative distance for EIGRP is going to be less than OSPF because, in theory, the metric is more accurate. Okay. We have a composite metric in the sense that it's a composite of multiple measurements. Okay. Bandwidth, reliability, delay, and load. So we have these K values. The default is K1 and 3 are set to 1, and the others are set to 0. And of course, 0 times anything is 0. Okay, so that those zeros essentially wipe those out. And so it just becomes uh, bandwidth and delay. Okay, bandwidth, it's the slowest bandwidth on the link. It's the bottleneck. Delay is cumulative delay of all of the exit interfaces added up. And the 256 is just it's when they went from IGRP to EIGRP. It's used to maintain backwards compatibility with IGRP, which in this day and age really isn't necessary because IGRP doesn't exist. Okay. Now, one thing to note, these K values are 8 bits, which means they can range from 0 to 255. They are not binary. Right? So if we really wanted to emphasize delay, we could set that to 10. Or, maybe K5, we're gonna set that to, 200, right? That'd be crazy, but in theory you could. Now, with super high bandwidths, this metric is a 32-bit number. That means once we get beyond very far after 4 billion, we've got a problem. Okay, and so when we have a network that has like high speeds, that's going to really mess up our metric. Okay, the lowest delay. Oh gosh, it's doing that thing again. The lowest delay that can be configured for an interface is 10 microseconds. Okay. Or high-speed interfaces channeled together will appear to be a single gigabit interface. To resolve this, we can use EIGRP wide metrics that support a 64-bit metric calculation. However, that's only used in EIGRP named configuration mode. Okay. Just kind of want to point that out. The book does talk about it in a little bit more detail, but it's a really simple concept, so I'll let you read it. I'm not going to spend a lot of time talking about it. Okay. Well, let's see. We are coming up on about 7:30. We will take a break here in just a few slides. So, oh yeah, okay. The variance command. Okay, so here we have this network. Okay. We are looking at this from the perspective of R1 trying to get to that subnet. Okay. And so R1 has a bunch of different paths that it can choose from. It's got 4 of them. Okay. And we see the cost of like each link, right? And it's always the outgoing interface, right? So if we went to the top one, it's 20, it's 5, and 5. So that's a cost of 30 if R2, right? But which one's the best? Well, if we add all those up, we can see our feasible distance, that's our metric. The lowest one is through R3, right? So that's going to be our best path. That's going to be our successor. Okay, so our successor is R3 with a feasible distance of 20. Okay, that's the way we're going to go. We've got a couple feasible successors, R2 and R5. Okay, R2 has a reported distance of 10, right? 5 and 5. Okay, and 10 is less than 20, which means we know it's not looping through us. Okay, same thing with R5, right? It's got a reported distance of 10 and that's less than our feasible distance of 20. So we know it's not looping through us. However, R4 is not a feasible successor because R4, you know, oops, 20 and 5 gives us 25, and that's too big. Okay. But so essentially, 3 out of the 4 paths here are totally usable because we know they're not loops, right? So we know we can't use this, but we can use the other 3. Now we are going to use R3 because, you know, that's our best path. But why not use these paths anyway? Well, by default, we are only going to do equal cost load balancing. That means if you have a best path that is essentially a tie with another path, you've got 2 best paths, then we'll load balance, right? Just like OSPF. But in our example here, you know, the metric of our feasible successors does not match our successor. So we're not going to load balance, but we should. Okay. Well, what we can do is we can change our variance. It defaults to 1, but we're gonna set it to 2 in this example. Okay. So what we're going to do is we're going to take our feasible distance of our best path and multiply it by the variance, and that means the metric of all of the other non-looping paths can be used as long as they're within the variance. So R2 gets added as a successor because its feasible distance, or R1's feasible distance, if it uses R2, is 30, which is less than 40. Okay. R5 is not added though, because our feasible distance, 40 plus 5 plus 5 is 50, and that's more than 40. How it would still be a feasible successor though. We're just not going to load balance with it. Okay. Now let me give you a what if. What if we set the variance to 3 and that became 60? What would happen to R4? Would we load balance with R4? Because 45 is less than 60.
Yes.
You might think, but remember, R1 thinks that R4 is a potential loop. That means R4 will not be load balanced with because it does not satisfy the feasibility condition, right? The most important thing that the routing protocol cares about is avoiding loops at all costs. So even though the variance of 3 would allow us to load balance with R4, we won't because R4 does not satisfy the feasibility condition. R1 thinks R4 is a potential loop, so it will never use R4 unless our primary route goes down and it has to recalculate everything. Okay. Now, when it comes to load balancing, we're going to load balance proportional to the bandwidth. And really, that should say metric. Proportional to the metric. Okay. So if we're doing R2 and R3, and so that means well, see the problem there, it's inverse. So the this is going to get something like, I don't know, somewhere around twice as much as, it's not exactly, right? If the metric was 15, then it would get exactly twice as much, but it'll get just shy of twice as much. Okay. So we got a metric of 30 and a metric of 20. So, that means the ratio will be, or 20 to 30, 2 to 3. One will get 1.5 times, looks like. Okay. Before I go on to route summarization, any questions on the variance command? Again, the variance command is one of those new things that EIGRP has that no other routing protocol has that allows you to unequal cost load balance. It allows you to make use of valid links that are just getting wasted, which makes EIGRP much more efficient as far as bandwidth is concerned. All right, route summarization. So EIGRP allows you to summarize, to send a summary route out of any interface you want. Unlike OSPF that says you have to do it on an ABR. The EIGRP says send it anywhere. Okay. And you can send a manual summarized route whether or not automatic summarization is on or not. Okay. So here we've got a slightly different topology. And R3 has these 3 routes connected to it, and it's advertising both of them, right? So if we look at the routing table of R1 and R2 over here, we can see all 3 routes are there. So we want to summarize this. Instead of sending all 3 routes, let's summarize them into one route. But we got to figure out what route we're going to summarize, okay? So we write them in binary. We figure out what the matching bits are. We have 22 of them. Okay, so we know we're going to have a /22. And so that's going to be our subnet mask. And then all the bits on the right of that are going to be 0. And all the left are going to be kept. And it gives us, you know, all of these are going to be turned into 0, right? So 192.168.0.0/22. So we're going to go on the interfaces that we want to advertise that network out. And we just configure the advertisement that we want, or the summary that we want to be advertised, right? So IP summary address, EIGRP autonomous system 1, and then the summary route. And that's going to be advertised out of that interface. And then we're going to do it on 2 different interfaces. Okay. If we look at our own routing table, it creates a null 0 summary route. Anybody know why it does that? Why is R3 going to create a summary route that goes to the bit bucket? Reason for that? Anybody got any ideas? I know you do. Come on. So let me give you a little scenario. All right. Let me see if I get kind of a, well, that's probably good enough. Okay. So let's just say for the sake of argument, let's advertise. So you'll notice this is also including 192. Oops, got like dyslexic all of a sudden. 192.168.0.0/24, right? And these 4 subnets, 1, 2, 3, 4, are being summarized in that network, okay? Because remember, we got, you know, if we look at here, 0, 0, we got 0, 0, 0, 1, 1, 0, 1, 1, okay? So we've got this 4th network that's being summarized, except we don't have that network. So guess what's going to happen? Let's say we get a packet to the .0 network. Okay, so let's say we get a packet to 192.168.0. something, you know, 10. Okay, well, these other routers are going to be like, oh, that's in this subnet, right? So they're going to send that packet to R3. What's R3 going to get? Okay, well, let's assume that this is not there. R3 is going to get a packet for this. Okay, and it does not have directly connect. It doesn't have a subnet for the 0. But let's say it has a default route, right? Because the internet's over here. Well, guess what? R3 is going to get this packet and it's going to say, well, I don't have a network like that, but I do have a default route. So I'm going to send it to R2. R2 gets it, sees this summary route and says, oh, that goes to R3. R3 gets it and says, oh, I have a default route. I'm going to send it over here. So, we end up with a routing loop. And that's what this does. This basically says if I get 192.168.0.10, okay, well, .1 has a /24. It'll match that before /22 because it's going to match the longest route, right? The more specific route. It's got a .3 and a .2, so this won't match any /24s. It will match this /22 though and get dropped. So the reason why we add this null 0 route whenever we summarize is to prevent routing loops. Okay. So now this, if we did have a 192.168.0.0/24 subnet, well then that would match that /24 and nothing would ever match this null 0, which is fine. Except, but why do we keep the null 0? It's not necessary then. But what if one of these were to go down? Then suddenly we've got a routing loop problem again. So that's why we keep it, even though we may not need it at any given point. All right. We can verify this by doing show IP route on R2 and R3, and we can see that we've got the /22s now instead of the individual ones. Okay, so this is going to reduce the number of total routes in the routing tables, which makes the lookup process more efficient. Also, summary routes that are being advertised take up less bandwidth for the updates because the update itself is smaller. Okay. Also, how do we calculate what the metric is? Well, we just pick the minimum metric of the constituent routes. And that's the metric of a summary route is the smallest metric of the routes that make it up. Does that make sense? What about automatic summarization? Now this is off by default, okay? This happens at a classful network boundary. So we got to figure out what is the classful network. Okay. So this is a class B. The default mask is a /16. So class B network. So what's the classful network that those belong to? If we were to say, which /16 network are those in? What would it be? Just convert this /24 to a /16. You can actually, if you just want to make it simpler, just look at one of them. But what, so this is a class B network, right? It's 172.16. So what classful network are they a part of? Which /16? Which /16 network would they belong to? Well, that's easy. Just kind of drop those. Okay. So these belong to the 172.16.0.0/16 network. Okay. So those all belong to there. What about this over here? Which /16 network does that belong in? Because that's class B as well. So the default mask for a class B, right, exactly, thank you, 172.17.0.0. Okay, so who cares? I know that's what you're asking yourself. I'll tell you. So over here, so we essentially have two different classful networks right here. You've got this classful network and this classful network. Again, who cares? Well, when we send an advertisement across that boundary, if automatic summarization is on, then we are not going to advertise each one of these /24s. We're going to advertise this /16 because the advertisement is crossing from one classful network to another, from the 172.16 to the 172.17. That means it's going to automatically summarize these. Without us having to configure it. And that means R2 is just going to see this one network. It's not going to see 3/24s. It's going to see 1/16. Does that make sense when we say automatic summarization at classful network boundaries? Everybody clear on that? Now, the thing is, we don't have super classful networks anymore. So you generally turn that off under router configuration mode. However, it's off by default. Okay. If you wanted to turn it on, use auto summary. So this is how it looks if we're not summarizing those different networks. Okay. Let's talk about propagating a default route really quick, and then we will take a break. Okay. So on R2, we have a static route. We can redistribute the static routes into EIGRP. That's not my favorite method, because now if you have another static route that you configure, it's also going to get advertised, and maybe you don't want that. Okay. Also, this is going to be an external route. We're taking a route from the quote unquote static routing protocol and putting it into EIGRP. That's going to give it an administrative distance of 170. Okay. And we might have to do route filtering, which we'll talk about in future chapters. Like if we have another static route that we're going to add to that maybe we don't want to advertise. So I would say instead of doing redistribute static, how about just make a summary address, right? On an interface, IP summary address, EIGRP1, and then default route. And this works even if there is no pre-existing default route in R2. And maybe R2 is running BGP and it doesn't have a default route. Well, then there's not going to be anything to distribute. Okay. I tend to prefer this method. Just use a summary address. Okay. And this is a duplicate. Well, actually, I'm not sure. So yeah, that last one was missing the slide, so I'll go ahead and go over it. So we can have 32 equal cost load balancing. 4 is allowed by default, but we can do unequal cost load balancing using the variance command. Okay, and it's a 7-bit number, so 1 to 128. Okay. All right. Yeah, so that's basically it. We saw all those. Okay, what about IPv6 come into play here with EIGRP? Well, all the routing protocols support IPv6. EIGRP supports it either way. Like with OSPF, we had to have 2 separate versions, where actually the EIGRP doesn't need a new version to support a new networking layer protocol, right? It has what's called protocol independent modules. So we can support any new layer 3 protocol that comes along, just kind of create a new module and just plug it in basically. Okay. So the basics of how it's going to work is essentially the same for IPv6. So if we look at this, Now, EIGRP for IPv4 is going to advertise IPv4 networks. EIGRP for IPv6 is going to advertise IPv6 networks. Okay. Still distance vector, still use dual. The bandwidth, the metric calculation is the same. Still uses reliable transport protocol, and that's a proprietary protocol that EIGRP created. Partial and bounded updates the same. So we're going to use hello packets to the IPv4 address for the neighbor discovery. And for IPv6, we use hello packets, and then we generally use the link local address for IPv6, not the unicast routing. Okay. The source and destination address for packets in general are going to be the multicast address. So in the case of IPv4, it's going to be 224.0.0.10 or FFO2::A for IPv6. One change with authentication, plain text authentication goes away with EIGRP because, what's the point? The router ID is the same. It's still 32-bit, and it doesn't matter if it's IPv4 or IPv6, okay? It's going to be a 32-bit router ID either way. All right. So we have an IPv4 network. We start by generating our neighbor table. Then once we get our adjacencies set up, we have our topology table. And then that's going to be used to populate the IPv4 routing table. Okay, well, we're doing dual stack. So we have an IPv6 network. Well, guess what? We're going to have an IPv6 neighbor table, then a topology table, and that's going to populate the IPv6 routing table. So you can think of this, there's an analogy, it's like ships in the night. They're both on the ocean and they're going back and forth, but they don't know about each other. It's like two different planes of existence. Okay, they're both going across the same network, but they don't affect each other. When it comes to EIGRP, and we're sending those messages, the source IP is always going to be the link local address. The destination address could be the multicast or the link local address, depending on circumstances. Okay. Now, there's two ways of configuring this. There's classic EIGRP for IPv6, and then there's named configuration mode. So we're going to look at the first one first because it's going to be more what you're familiar with. So here's our topology. Okay, so we've got R1, R2, R3, and then an ISP. Just to kind of keep things simple, for IPv4, we're just using /24 links and /64 links for IPv6. To IPv4, these are usually going to be a /30, right? But don't worry about that. We're not going to split hairs. So on R2, the one in the middle, we've got it highlighted. We're going to issue a show IP interface brief, and we can see we've got our interfaces, okay? So serial links are going to be assumed to be a LAN interface here, but this is just a weird interface, so or a weird topology, so don't worry about the serial links versus Ethernet links. Okay, show IPv6 interface brief. Okay, so we've got this interface and that interface. IPv4 addresses, IPv6, right? Link local. So what we're doing here is we're doing FE : router number. So both link locals on both are going to be FE80: 2. Over here, it's going to be FE80: 3 on both sides, et cetera, et cetera. Okay. So that's essentially what the IP configuration is for all of the routers. So let's see what EIGRP for IPv4 looks like on the routers. Okay. So we're not including any WAN interfaces at this point. So router EIGRP1, there's the router ID. We're using network commands. We're using the classical networks, right, for the two interfaces. doing the same thing over here and doing the same thing over here. Here we have a static route for a default route, and then we're going to redistribute static. So we're going to take all those static routes and put into the EIGRP routing protocol. Okay. That to be advertised. So if we verify R1, we can see that we have 3 routes, right? This is directly connected, so that's not going to be an EIGRP route. Okay, so we've got this route, that one, I should say destination, along with the default route. Okay. Now, to configure IPv6 for R1, we have to turn it into a router by saying IPv6 unicast routing. Now, this is on by default for IPv4. Okay, but you got to turn it. It's not on by default for IPv6. You can assign an IPv6 address to an interface without this, but it's not going to route. Okay, it's going to be like a host. It's going to be like if you put an IPv6 address on your computer, you can ping it. It can send and receive traffic as far as if it's the one end of the destination, right? If it's the destination or if it's sourcing it, but it won't take IPv6 traffic from one interface and send it out of another interface. Okay, it needs to be a router for that. So we turn on IPv6 unicast routing so that we don't get an error when we try to do this. We go to IPv6 router EIGRP2. So we're giving it autonomous system 2. So here we're specifying it's IPv6. Okay. The autonomous system has to match all the other routers for this to work. Okay. We give it a router ID. Notice it's the same 32-bit router ID. If there was no IPv4 addresses, because remember, it can figure out its own router ID if you don't configure it. It's going to do the highest IPv4 address on a loopback, whether it's up or not. If there's no loopbacks, it'll do the highest IPv4 address on an active interface. Okay. If you were in a situation where IPv4 was not configured, you would need to configure this or you'd get an error. Then we have to do a no shutdown. Don't forget this on labs and stuff. This is easily forgotten. The EIGRP process starts in a shutdown state for IPv6. This is different than if you're dealing with IPv4. Now, this is not necessarily required. I just remembered this is actually required on some older iOSs. Okay, you can if you want to make some changes, you can shut it down, or I guess you could just issue the whole shutdown command if you want to temporarily suspend the EIGRP process without like deleting all of the configuration. Okay. Go into the interface. Now we are not going to use the network command. We've done away with the network command, which I think is awesome because the network command is confusing and problematic. Now we're just going to go into the interface and say IPv6 EIGRP autonomous system 2. We're just saying, hey, interface, you're participating. Okay. Now, strictly speaking, you actually don't really have to do this because as soon as you create this, all IPv6 interfaces are going to participate automatically. Okay. But it's good practice to do it anyway. Okay, so that was R1. Let's look at R2. Pretty much the same thing. Router ID is going to be different. We're going to make the interfaces participate. Okay, that's it. R3, same thing, unicast routing. Now this one has the default route, right? IPv route, all zeros, next hop IP. IPv6, router EIGRP2, then the router ID. We're going to redistribute static, so now this gets advertised. We're going to make sure the necessary interfaces are participating. Okay, notice we did not go into this interface because we are not advertising that network. That's what the default route does. If we go back to R1 on the left, do a show IPv6 EIGRP neighbors, not show IP EIGRP neighbors. Now it's show IPv6 EIGRP neighbors. Okay. So notice the link local address. It's specifying the link local address, but notice we also need to know the serial interface. Because remember, the link local address is not in the routing table. Whenever you're dealing with link local, you always have to specify the interface. Okay. And in this case, it's the interface that it was the update was learned on, the hello that we got from the neighbor. Okay. Show IPv6 EIGRP topologies. Okay. Notice the next hop is the link local. And in this case, it's of R2 because that's, the only router that we have. Okay. The feasible distance and the successor's reported distance. Now, in this case, it's not like we have alternate paths anywhere. So the reported distance, again, is meaningless because there are no backup links, so there's no backup routes. Now, let's look at the routing table. Limit it to the IPv6 routes. Okay. So again, because we're only EIGRP routes, we're not going to see the connected route there. We'll see this one, and the default, right? There's the default. Notice it's an external route because we did a redistribute static. Its administrative distance is 170 instead of 90, right? And then we've got those two subnets, okay? Again, the next hop is always the link local address, okay? Administrative distance and the metric. Now, there isn't the issue of automatic summarization for IPv6 because automatic summarization has to do with classful networks, and IPv6 doesn't, there's no concept of classful networks in IPv6. All right. So we've got these /64s that we want to summarize. So how do we do that? Okay. By the way, we would create these. We would create loopback interfaces in order to simulate those if we were actually configuring this in a lab. So the summary address is configured the same: IPv6 summary EIGRP2 address. Right. So we're summarizing those 4 64s into a /62. Okay. So that summary address is configured on R3. So we're going to go to R1 and see if we can see them. There we go. There's that /62, 2001 DB8 F0. Okay. R3 do a show IPv6 protocols. We can see that we are doing redistribution of static routing so that we have that default route that's going to get advertised. We can see we have that summary route of those 4 networks also. Okay. And remember, the metric for that summarized route is going to be the lowest metric or the best metric of any one of those. We look at the metrics for each one of those, and the best one is the one that we're going to use. Okay. So let's see a summary of what we've got so far. So in R1, we've got an IPv4 address on the 2 interfaces. Okay. We've got EIGRP for IPv4 configured, right? Router, network, router ID. Okay. Then IPv6 addresses. Now at this point, if we tried to configure routing, we'd have a problem. Okay, we'd get an error. We need to turn it into an IPv6 router first. Once we do that, then we can configure IPv6, and all we do is give it a router ID. Technically, we wouldn't even have to do that because we have IPv4 stuff going on, but we wouldn't have this nice, neat router ID. Okay. Then we're going to make these 2 part of the process. All right. So you can see that configuring EIGRP for IPv6 looks very similar, maybe with the exception of having to do the unicast routing and then this instead of the network commands. But other than that, it's very similar. Okay. Now let's look at named EIGRP configuration mode. All right. So with Classic, you're going to have two EIGRP configurations going on. One for IPv4 and one for IPv6. In named EIGRP configuration mode, it's a newer mode, and you're going to gather both IPv4 and IPv6 into kind of a single space. We're going to use address families for IPv4 and IPv6 under the EIGRP configuration. All right. If you're going to use EIGRP for IPv6 and virtual routing and forwarding, you have to use named configuration mode. The idea is at some point, someday, we're just going to do IPv6 in named configuration mode. So in the meantime, dual stack using named configuration mode. Okay. IPv6 unicast routing. In theory, you could do multicast routing also if we were doing multicast routing. Okay. So this turns on the IPv6 router magic powers. Okay. And then we're going to go into named configuration mode. So we're going to name it something. Router EIGRP dual stack. Okay. So this does not have to match other routers. And then we're going to go into the address family. If we hit the question mark, we've got two choices, IPv4 and IPv6. Okay. So IPv4, right? And then here you'd have some choices, unicast, multicast, right? We're going to do unicast. Okay. Autonomous system 1. This must match the other routers for this autonomous family. Address family, not autonomous family, address family. Okay. Then we're going to now we're in address family configuration mode. That's like the main EIGRP configuration mode was in Classic. Okay. In IPv4, we can still use the network commands. Okay. Although you can also just go straight to the interfaces, even for IPv4. Okay. For IPv6, it looks pretty much the same. Okay. These don't have to match each other, but they could, because again, ships in the night, right? But they do have to match the numbers for their corresponding address families on the other routers. Okay. So if we're going to set IPv6 to 2, all the other routers have to be 2 for IPv6. Okay. And again, like I said, all IPv6 interfaces are enabled for EIGRP in named configuration mode. Okay, so let me get a blank slide because this is cool. It's mind blowing. So new slide, blank. Okay, so let's say I have routers. I've got different subnets, right? Okay, so here's the scenario. We're not going to put unicast routing addresses on any interfaces except for these subnets. Okay. So remember, link local addresses are required for IPv6, but you don't have to set them. Also remember, routing protocols use multicast addressing or link local addressing. We do not have to have a unicast address assigned to it. Okay. A global routable unicast. Also remember, EIGRP, all interfaces participate automatically. So that means, we set an IP address of something, 2001, here, 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 here. We turn on EIGRP. We don't have to use any network commands. We don't have to make the interfaces a part of it. And, On these routers and on these interfaces, there's not even globally routable IP addresses, IPv6 addresses. But what's funny is EIGRP will work and we'll be able to route a packet from one subnet to another, even though we don't have any globally routable unicast addresses on these routers. Now, here's the thing. We can route packets through the routers, but if I'm over here on this subnet, I would not be able to telnet there because there's no destination address I can reach, but it will route my packets just fine. I've never configured an IP address anywhere on that router. I never manually made any of the interfaces part of EIGRP, yet it still works. And that's just kind of mind blowing if you think about it. I think it's so cool. It almost turns routing into about as close to plug and play as you can get. It's like, all right. So let's configure named EIGRP. Well, actually, did I? Okay, no, we got done with that slide. Okay. Okay. So named EIGRP configuration for R2. Unicast routing, we're going to name it dual stack. IPv4 autonomous system 1's got a match. Now at this point, this network command for IPv4, made that start to participate. And so then we get an adjacency. Then when this one participates, we don't have an adjacency yet because R3 hasn't been configured. Okay. We go IPv6 address family, autonomous system 2, router ID. Once we do this, we get an adjacency immediately because remember, as soon as we entered address family configuration mode, this became a member, and so did this automatically. Because remember, I said for address family configuration mode for IPv6, interfaces participate automatically. All right, R3 unicast routing, et cetera, et cetera. Got the router ID. Okay. We as soon as this network statement came up and that started participating, we got a neighbor adjacency between R2 and R3. But you notice as soon as we started IPv6 address family, we got a neighbor adjacency, serial 001, right? Out that direction, even before we had a router ID configured. Okay. Then we've got the default route for IPv4 and a default route for IPv6. We're going to go into dual stack. We're going to configure IPv4. Now, if we go into the topology configuration, when we hit the question mark, this is where, you got your auto summary, your redistribute, your variants. Okay. That's what we're going to use. So we've got the default route and we need to redistribute that. Okay. So we go into topology base, redistribute static. Then we're going to go into IPv6 address family configuration, topology base, redistribute static. Okay. Now we do a show IP EIGRP on R1, IPv4, right? We've got the static route and we've got those IPv4 routes. Okay, so 3 routes in total. Okay. Now this network over here is not advertised because we didn't include that interface with a network command, right? Makes sense. If we're on R1, we do a show IPv6 routing table. Okay. Now we have this static route via FE80::2 out serial 00, right? The 77 subnet over here. Oops, wrong one. Oh, I'm covering it up. 77 subnet over here. The Cafe 3, which is over there, Cafe 4 over here. Now notice we do have that one. Why are we seeing that route? Keep in mind, we did not see that route in IPv4. So why are we seeing this one being advertised over here on R1? Well, remember, all IPv6 interfaces are enabled automatically. So as soon as we turned IPv6 on over here, this interface started participating and started advertising that out. Most of the time, that's fine. But in this case, we don't want to advertise that. That's why we have the default route. Okay. So how do we remove this IPv6 prefix from being advertised? All right, well, instead of using the network command, or instead of making an interface participate in EIGRP, we actually kind of take an opposite kind of approach. All right, so we go into EIGRP configuration mode, the IPv6 address family, okay, and then we go into that interface, address family interface configuration mode, and we shut it down. That's like the equivalent of not using a network command. Okay. If we do a show IPv6 interface brief and look at serial 010, okay, we can see it's up and it does have IPv6 addresses. Okay. Even though we issued a shutdown command, it only shut it down inside of EIGRP land, right? It's still up as far as networking is concerned. It's just not enabled for EIGRP for IPv6. Okay, so if we verify that on R1, now we can see that 77 subnet is no longer in R1's routing table. Okay. Family on the interface, what options do we have? We actually have a lot. If you want to set off authentication, if you issue the default command, it'll set that interface straight down to its defaults. Okay, so it's like issuing no's on any commands that might be there. Hello and hold time, passive interface. You know, maybe again, you do want it advertised, but you don't want it sending hellos, right? Shut down, disable that address family on the interface for EIGRP purposes, right? If you want to do a summary address. So this address family interface configuration mode for that interface is where you do all of these things. You don't actually go to the physical interface anymore. Okay. All right. So we want to make, you know, that passive and that passive, right? Because there's no routers out there to send hellos, but we still want to advertise those networks. Okay. So on R3, we're going to go into address family IPv4, the address family interface configuration mode, issue the passive command. Then we're going to do that same thing for the IPv6 address family configuration mode. Okay. And this does kind of seem complicated at first, but once you get used to it, it makes it easier in the long run because now you're not having to go to, you know, EIGRP for IPv4, EIGRP for IPv6 in two different places in the configuration. You're not having to look at all of the interfaces, right? We're not going to the physical interfaces anywhere to configure anything. It's all under this one heading now. Then we go into R1, we go in, you know, IPv4, interface passive, IPv6, interface passive. All right. We're going to advertise these summary addresses. Okay. Address family, interface, summary address. Now look at this. Yes, you can use CIDR notation. Finally. Isn't that about time? Again, how long has it been? you can finally use slash notation in your configuration for IPv4. And of course, you can do it for IPv6 as well. Okay. So address family IPv6, interface, summary address. Again, CIDR notation. If we want to verify this, we can do show IP route EIGRP. So this is IPv4, okay? And so we can see there's the default route, right? The 10.summary route, the 192.168.3 right there, and the .4, okay? We don't see these because they're directly connected, which makes sense, okay? For IPv6, same thing. We have the default route, and then we have, this summarized route over here, right? Notice it's the /48 instead of a 64, okay? And then I'm not showing it, but we've got those routes as well. So if we do a show IP protocols here, we can see here we're doing the redistribute static on R3 because that's the one with the default route. There's the router ID. If we keep going, the 10 dot. Now remember, this is just IPv4, so it's not going to. It's only going to show the IPv4 address. The routing for the networks, okay, and then those are the network commands. We do have one passive interface, okay. If we look at the IPv6 side of things, okay, router ID is the same, and if we keep going, we can see those are the interfaces, but now this is listed under interfaces, but it's listed as passive, which I think is a better way of doing it, okay. We're redistributing static, and there's our address summarization. Okay, so this show IP whatever protocols gives you a lot of information. And I'd like to point something out. I haven't really mentioned this a whole lot, but I'll probably harp on this. Don't get in the habit of doing show run for everything. That will get you in trouble, because what show run does is it tells you how something is configured, but it does not tell you how it's operating. Okay. And if you rely on show run, you're going to have a hard time. Okay. Oh, and also gigabit 01, by the way, is not listed here because remember, that was the one that we shut down. That's the WAN interface. So it's not listed at all. All right. So let's take a look at the interface overall. Almost done, guys. Getting really close. R3 configuration. All right, so IPv6 unicast routing. There's our main EIGRP named process. IPv4 address family, autonomous system 1, our network commands and our router ID. We're going to make the one interface passive. There's our summary address, and we're going to redistribute static. For the IPv6 address family, autonomous system 2, EIGRP, there's our router ID. Okay. We're going to shut that interface down. Probably should have had that show up in order. That might be a little confusing. That interface is going to be passive, right? So that's address family interface configuration mode. Okay. That interface, we're going to be sending a summary address out. And then we're going to do redistribute static as well. Now, what we're not showing here is the default route that we have configured, the static route that we have configured. Okay. All right. So classic configurations, right? Separate. And then this is configured on the interface directly. For named EIGRP configuration, EIGRP, here we've got the overall EIGRP, and then we have IPv4 and IPv6. Notice nothing on the physical interface. All right. Now let's talk about EIGRP authentication. Now the cool thing is we use there's the concept of keychains. All right, we name a key And then we have a keychain, we name it, and then we have different keys on there, which can have different strings. They can be valid at different times. Now, EIGRP can refer to this keychain. So can OSPF. So can other things. So you can have multiple keychains defined, and different protocols can refer to different keychains. So technically, this keychain is separate from the EIGRP configuration, but the EIGRP process can refer to that configuration, to that keychain. Okay. Now, we did not set any lifetimes, so they're always valid. Okay, so we're going to configure them on R1 and R2, and we have a matching secret, right? Because R1 and R2 are going to need to talk to each other. All right. So on this interface, we're going to say IP authentication mode EIGRP 100. That's the AS we're using now. MD5. And then we're going to tell the keychain to use. Okay, so the authentication method is not tied to the keychain. We're using MD5 here, and then we're saying use these keys. Okay, and then we do that on R2, and we're good to go. Okay, and we know it worked because we have a neighbor relationship. There's not like a command to say, is authentication working? Well, if you have set up authentication and they're neighbors, then yes, it's working. Okay. So the pre-shared key. Of the two keys so that you can change the keys without actually having any downtime. Okay. So whenever you change the authentication, it will go down for a second, but it'll come right back up. Okay. Once you've got this, though, if you add a key and then, say you retire a key, that doesn't change this. This command is what makes the relationship go up and down. Okay. So here we're doing it a little different. This is IPv6. But you can see that the commands are pretty much the same, right? The only difference is IPv6 rather than IP. Very, very, very similar. Okay. Now let's look at named EIGRP authentication mode. Okay, we make a keychain. Again, remember the keychain is separate. The keychain has nothing to do with EIGRP. It's just EIGRP is going to reference the keychain when it needs to. Okay, so we're going to go into our named configuration mode, address family 4, and then the address family interface configuration mode. We're going to tell it the key, and then we're going to tell it the mode. So now we're using SHA-256. Okay, so that's going to reference the keychain. All right, and again, the nice thing here is the keychain is separate because that's a separate thing from EIGRP, but everything else is going to be under EIGRP configuration mode. This stuff is no longer found under the interface. Okay, and it may not seem like a big deal, but if you ever have to manage a router that's kind of complicated, it's really helpful to have all your routing configuration in one place rather than having it spread out all over the configuration file. Okay. That's it. Woohoo! So remember, the good news is we did part of chapter 3 and pretty much all of chapter 5. So it's kind of long tonight, but we'll benefit here in a couple classes coming up. Any questions or anything on this?